For the second half of 1.4 in your textbook, and again, this is Linear Algebra and its Applications by David Ley, we want to talk about the computation of Ax, which is going to look a little bit more like the normal way that you would multiply matrices. So we're going back to an example that we did previously, and we found our solution to be 117. And we did that, again, by using our vector as the scalars. So 2 and 3 and -1 were the scalars for column 1, column 2, and column 3 of our matrix. So now we're going to look at the row vector rule for computing Ax. And that says if Ax is defined, the ith entry of Ax is the sum of the products of the corresponding entries from row I of A and from the vector x. So what all of that is essentially saying is that I'm going to take this row times the column, and that's going to give me this solution of 1, and I'm going to take the sum of this row times the column, and that's going to give me the solution of 17. So let's take a look at what that looks like. Essentially, it's saying take the first entry times the first entry. So 2 times 2, and yes, I'm going to do this the long way, and then -1 times 3, so plus -1 times 3, and then 0 times -1, so plus 0 times -1. And again, we know exactly how many things we're going to have here because we have, this is a 2 by 3, and this is a 3 by 1, and we know, hopefully we remember, that these values must match up for us to be able to multiply them, and our resulting matrix is then going to be a 2 by 1. So that's how I'm going to end up with this 2 rows, 1 column. Before I do any of that math, I'm going to go ahead and move to the next row. So I'm going to take the first entry times the first entry. So 3 times 2 plus 4 times 3 plus 1 times -1. And again, then I'm just going to do the math. So that's 4 plus -3 plus 0. And on the bottom, I have 6 plus 12 plus -1. And then my solution is 4 plus -3 plus 0 is 1. And 6 plus 12 minus 1 is 17. So again, this is probably what you're used to with multiplying matrices, but that is how we get it, is the row vector rule for computing Ax. I have 2 practice that I would like to go through with you, 2 pages of practice, so 2 questions on this page, 2 questions on the next. And essentially the purpose of that is just obviously to give you practice, but also to demonstrate a property. So I'm not proving this property. You can prove that these two are equivalent, and I'm not going to do that. There is a proof, a formal proof in your textbook, but we are going to do an example that essentially shows that those two values would be equivalent. So here I have matrix A, and then I've got vectors u and v, and the first one is telling me obviously that I'm going to take A and I'm going to multiply it by the sum of u plus v. And obviously the way that it is written tells us, because it's order of operations, and we all know order of operations, that we're going to have to first add the matrix or the vectors together. So -4 plus 3 is -1, 2 plus -1 is +1. And now I'm going to use that rule that we just talked about to take 2 times -1 plus 1 times 1. So first entry times first entry, and then second times second. And then for my next row, I'm going to take row 2 multiplied by the values in the vector. So -4 times -1 plus 2 times 1. And that's going to give me negative 2 plus 2, plus 1, and then positive 4 plus 2, so my solution is negative 1, 6. Now, unless I've made an error, then hopefully when I do this second question, I should also end up with negative 1, 6. And this one is saying, let's take 2, 1, negative 4, 2, and multiply it by negative 4, 2. And then let's also do the exact same thing with vector v, which is 3, negative 1. So again, I would take 2 times negative 4 plus 1 times 2, and negative 4 times negative 4 plus 2 times 2. And I would add that to 2 times 3 plus 1 times negative 1, and negative 4 times 3 plus 2 times negative 1. This would give me negative 8 plus 2, 16 plus 4, 6 plus negative 1, negative 12 plus negative 2. So now I have negative 6, 20, plus 5, negative 14. And when I add those together, I get negative 1, 6. And we can see, again, we have not proved, but we've just shown an example that this is in fact true. So again, one of the properties is that these two expressions are equivalent. Here's a similar practice for you to try on your own. And again, we're not doing a proof that these two expressions are equivalent, but we're showing an example that these two expressions are equivalent. So press pause, go ahead and work through each of these, and then hopefully at the end you have the same solution and you've shown that they are equivalent. So here again we have A, which is our matrix, and C, which is a scalar, and then U, which is a vector. So this is saying, let's take A, and we're going to take 2 times our vector first. So before we multiply it by A, 2, 1, negative 4, 2, I'm going to take 2 times vector U, which would give me negative 8, 4. And then I'm going to go ahead and do that multiplication. So 2 times negative 8 plus 1 times 4, and then negative 4 times negative 8 plus 2 times 4. And that gives me negative 16 plus 4 and 32 plus 8. And that gives me negative 1240. So hopefully when I do my second question, I end up also with negative 1240. So this one is saying, let's take 2 multiplied by A times U. So I'm going to take the 2 on the outside. I'm going to multiply 2 times negative 4 plus 1 times 2, and then negative 4 times negative 4 plus 2 times 2. And that's going to give me 2 times, this is negative 8 plus 2, and this is 16 plus 4. So that gives me 2 times negative 6, 20, which gives me negative 1240. So yay, I got the same thing twice. And again, we did not prove that these two are equivalent. That proof is in your textbook, but we have shown that they are in fact equivalent.